Yes, so welcome back, everybody. Let's get that last big push to the Christmas break. Let's take a look at what we have on Buzz this week before we wrap up. Get the finals. All right, 0B right here. Let's go to our grade screen as usual. Let's see what got. All right. So before the break, we had the first two lessons on exponential functions and log functions. Now we have properties of logarithms today, along with how do we solve exponential equations that don't have the same base, because we were looking at log functions and solving them before if they had the same base, but how do we do it when they don't? And then next week we'll have graphing of both functions. And then we'll be at the end of the semester here. We got the semester final coming up. I'm thinking at this point, I'm just going to wrap the test for this module into the final and maybe not do it separately. Just make that part of the final, which would benefit some of you guys because this is the class you can exempt. Algebra 3 is not a required final. Algebra 2 has to take the winter final. Algebra 3 does not. So you can exempt. If your grade is above 75%, you don't have the 4 absences, you don't have any missing assignments, you haven't had more than 4 absences in advisory, all of those exemption requirements. This is a class you can exempt from and not have to take the final at all. Hey, we like that idea. So let's finish strong here. Everybody get your grade where you want it and don't have to worry about the final. So let's look at 4.03, 4.04 this morning. Back to activities. Close module 3. We're done with that. All right, properties of logarithms. All right, we probably need to refresh ourselves on what we did the week before the break, because if you're like me, you're totally zoned out for the break and don't remember anything. It's like, what class was we in before? Yeah, so we will pull this up right here and take a look at that real quick. All right. So if we remember, we were looking at logarithms and exponential equations. And so with a logarithm, we'd have log, and it had a base, right? Log base b of y equals x, right? We have something that looks like that. In a practical example, let's say we have log base 7 of 49. Where this is the base and this is the argument. All right. So something like that. And we're like, how do we solve that? Well, we can rewrite this as an exponential equation, right? The b is the base. So that would be the base of our exponent. And this over here is our exponent. So b to the x power equals y. So in this example, 7, let's see, this is actually equal x to the x power equals 49. We just take whatever's there, move it on the other side, the equal sign. So we'll kind of make sure the base is the base. The base stays the same. So it's just where do things go? So now we can solve that. And we say, oh, well, 49 is 7 squared, right? That's what 7 squared is. So 7 to the x equals 7 squared. So x equals 2. Remember, if we have the same base, we can just set the exponents equal to each other. X equals 2. So in this, x equals 2. Log 749 equals 2. So that's a little review of what we did the week before Thanksgiving. Is when we solve logarithms, we can rearrange them and set them as an exponential, which we're more familiar with exponential equations than we are logarithmic equations. But they are inverses of each other, right? It's kind of like multiplication and division. They go as a set. If you have exponential, and remember exponential, it's only an exponential equation if the variable is in the exponent. If it's x squared, that's not an exponential equation. That's a quadratic equation. But the variable has to be up in the exponent for it to be considered an exponential equation. So with that little review, let's move on to, oh, wait, am I in the right? Yeah, properties of logarithms. Yes, just making sure. Because they're talking about different bases. That's next lesson, actually. So a logarithm with a base of 2 is used in computer science because it connects the binary numeral system, right? A logarithm with a base of e, remember e is 2.71818. It's used with interest rates to determine a specific amount of growth has occurred, especially in like bacteria and things like that, because it's continually growing. So a log with base e is called a natural logarithm. Remember that? It's abbreviated ln, right? Log base e is just abbreviated ln. A logarithm of the base like 10, which is the standard, because we have a number system based on 10. So log on a calculator, if you don't write the base, it's assumed to be 10. That's used in the Richter scale for determining the strength of an earthquake. That's called the common logarithm, just base 10. So on a calculator, that button that has log, that's the common log. That's base 10. That's base 10. And we can see that on our calculator, even on the computer here. We have this log button, but it doesn't have a base. That means this is a base 10 button right there. So if we said 100, what is the log of 100? It's 2, because 10 squared is 100. So it says log 100. See, on this calculator on the computer, and I'm not sure if your Chromebook's the same way or if the calculator in Buzz is the same way. This one, you have to put the argument first before you hit the log button. If I hit log without hitting an argument, it says invalid input because it can't take the log of 0. Because 10, there's no power of 10 that would equal 0. 10 to the 0 power, 10 to the 0 power is 1. So on the computer calculator, you have to hit the number first. I want to know 1,000 log, it's 3, just 10 to the 3rd power. So just be aware of that. You may have to hit that first. The way to test this, just hit the log button and see. Then you'll know, okay, well, I have to hit the argument first before I hit log. Okay, let's go to page 2. It says there's 10 pages to this lesson, but most of those are practice problems because you need lots of practice with logarithms because we don't do them very often. All right, the change of base formula. All right, this is a great thing to have in our notes. I'm gonna show it on paper rather than going through the way they do all of on Buzz to start off here. So change of base. This is a great notes day. There's several things to put in your notes that will be useful when you take the final or you take an assignment or you do a quiz or a test, whatever it is. But the change of base. So I'm going to underline it, change of base. So if we have, let's say log base 4 of 71. And we want to know what does that equal? Well, 4 to what power equals x? 4 to what power equals 71? Well, it's not going to be an integer, right? Because 71 is not going to be 4 to the 3rd, 4 to the 4th, 4 to the 5th, nothing like that. It's going to be some decimal number. And we look at our calculator and we go, well, the calculator is not going to help me. Actually, it does have that ability because if you hit the second button, it does let you put the base on there. But we're going to say we have a very plain calculator that only has the log button. So that's base 10. Well, this is not base 10, so I couldn't put that in a calculator. I have really not a good way at all of finding this. Well, the change of base, I can rewrite this as log 71 divided by log 4 equals x. What base are these? Those are base 10 because I didn't write anything. If I don't write a base number, these are base 10. So it's taking the argument and it becomes the argument at the top and the base becomes the argument at the bottom. This we can do in a calculator. Let's put our calculator up here. So log 71 divided by log 4. So 71 log, which is 1.8512583, divided by 4 log. Okay, so this equals 3.075. We'll go 3 decimals because the 4 would round up. 3.075. So 4 to the power of 3.075. Because we know 4 to the third power, 4 times 4 times 4 is 64. So that'd be close. Like, oh, that's pretty cool. 3.074. Let's test it since this calculator can do, I can do log base. But I have to, let's see, I got to put the argument in first, I think, if I remember correctly. So if I do the 71 log base, oh, I didn't hit the right button. 71 second log base. It's asking me what base for, if I did that correctly. Yeah, 3.0748. Yeah, that's the same number. So 71 log base 4 is 3.078. That's the same thing we got using base 10. So this is a very useful thing to know, is the change of base, where we can take any base and do it with a plain calculator that only has the base 10. So we'll highlight that. It goes right up there. And then the base goes at the bottom. So very good to have in our notes right there. By the way, while we're talking about that, what if we had the natural log? Natural log of 8. What is the natural log of 8? Well, remember, that is the same as saying log base E of 8. And you're like, what was E? Well, our calculator, if we want to know what E is, it's got an E button. E equals 2.718281828, blah, 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 blah. It's like pi. It never ends. So if I want to know, well, what is this? What power do I raise this to get 8? ln of 8. So if it's log base E, we don't write log base E. We just write ln, natural log. But we could do the same thing on that. This is the same thing as log of 8 over log of E. Base 10. Log of 8 divided by log of E, which equals, let's see. So 8 log divided by E log 2.0 880. We'll again round it to 3 decimals. Yeah. So if we take E to the power of 2.08 or 0.794418, it'll end up being 8. Now, I don't want you to think that we can always just convert to log 10, because this works with any base. Change a base formula. If we have log base 3 of, let's just do 44. We could change that to log base 5 the same way. Take the 44, put it on top, put the 3 on bottom. Just change it to log base 5. It'll work with any base as long as you use the same base over here. You can change it to any base and still be right. Let's do log 5 of 44 at our calculator using the second button. All right, so 44 log base 5 divided by 3 log base 5 is 3.44, and we'll round the third digit up to a 5 since the next digit is a 5. So is that correct? Well, I don't know. Let's put this in our calculator and double check. So use that second button. So 44 log base 3. Oh, look, 3.445. Same number. So it works regardless of what base you put there. It's just the reason that we generally do this is because that's easiest on our calculator. Our calculator has a log button. Even the most basic calculators generally have a log base 10 button. So that's what we commonly default to, is going to log 10. But it works with any base. So that's what I want you to understand. It doesn't have to be log base 10. It'll work regardless. Change of base. Your base. Yes, Sid.
Where did the 5 come from? I'm kind of
I just
confused.
I just picked it. I decided what base do I
Oh,
want to use. So
oh, okay.
yeah, that's what I'm saying. If we have log 3 of 44, I can change it to any base I want to. So I decided to change it to log base 5.
Okay, so it doesn't matter. Like, it doesn't have to be like a certain number.
Nope. You can pick
Okay,
whatever. Yeah.
okay.
As
Thank
long
you.
as yeah, as long as you get these numbers correctly, the 44 goes on top, the 3 goes on the bottom. You can pick anything. That's why I say usually we just do log base 10 because that's the
Okay,
standard. But yeah, we could do log base
okay.
98
Thank you.
if we want to. You're welcome. That's a good question, though. It's a very good question. So yeah, we could do log base 98 if we want. Just doesn't matter. Just saying you could pick any number you want if you're doing the change of base. But we do commonly pick the 10 because that's easiest on our calculator. And it's easiest in our thinking. We think base 10. We use 10 as our base number system. So all right. What else are we going to look at? Let's see what they're doing. Oh, this talks about the calculator where you may have to hit the log button first, or you may have to hit the argument first. So we looked at our calculator, see that. Let's see. Which logarithmic expression results in a solution of 3? Okay, so this wants us to do a little calculator practice. So if you have a calculator there with you, you can do this as well. But we'll look at it. Let me go wider. All right. So log 2 plus log 8. Let's see if that equals, results in a solution of 3. Does that equal 3? Log 2 plus log 8. No, it equals 1.2. So it's not the first one. How about the second one? Log 2 minus log 8. Log 2 minus log 8. Nope, that's negative 0.6. Log 8 minus log 2. We'll do it the other direction there. So log 8 minus log 2. Now that's a positive 0.6. Yeah, we should have known that. If it was a negative subtracted that way, it's a positive the other way. How about if we multiply them? Log 2 times log 8. Now that's 0.9. Well, let's see if we divide log 2 by log 8. So let's see, log 2 divided by log 8 is 1.1. Oh, I got too many things up there. Wait, clear. Log 2 divided by log 8. It's not 0.1, it's 0.3333. Oh, that gives us a good feeling that if we divide the other way, it's probably going to work. All right, log 8 divided by log 2. That one equals 3. Right there. If we divide log 8 by log 2, it equals 3, which makes sense. You're like, what do you mean that makes sense, Mr. Brock? Log 8 over log 2. I wrote that down here. If we're looking at log 8 over log 2, thinking about the change of base, if we change it back to this form, that would be the same as log base 2 of 8. Right? Just go in the other direction. Take the bottom one and make it the base and the top on that. So this is asking 2 to what power equals 8? Yeah, 2 to the third power equals 8. So we would expect log 8 divided by log 2 to equal 3 because the change of base is it's just asking this. So you can go either direction with it because we know that this equals that. So just throwing that out there. Close that back down. All right, shut that back down. Okay, so the change of base formula is right there. Log b of y equals log y over log b for any basis. So again, that's great in your notes. And with the natural log, we looked at that. Oh, well, they just want us to do that. Natural log with the ln, we can use that as well. So what happens when the base of a logarithm is the same as this argument? Oh, that's a good question to think about. What does happen when the same base as the argument? If I said log of base 91, I'm going to do something real complicated, right? Of 91. What's that going to equal? Or make it more simple, log 3 of 3. Or just log of 10. What's your thoughts? Those all have the same answer, by the way. What is log 91 of base 91? Log base 91 of 91. Log base 3 of 3. Log base 10 of 10. Any thoughts on that? I'll let you think about that for a moment. Put that in the chat if you think you got it.
Can you repeat the question one more time?
Sure. I'm going to put these notes on here up too. Down here at the bottom, log 91 of 91 equals what? If it's base 91 and the argument's 91, log base 3 of 3 equals what? Log base, well, that must be base 10 because I didn't write anything. Log base 10 of 10. All of these equal the same thing. I'm going to put those notes all the way up at the top. This will give you a good clue. I'm going to let you ruminate. I got a couple people putting things in the chat. So what's this asking? If we look at this, it's saying B, the base, to what power, because that's on the other side, to what power equals the argument. 91 to what power equals 91? To the first power. 91 to the first power equals 91. 3 to the first power equals 3. So that's a 1. That's a 1. Those are all 1. If you have the same base as you do the argument, that's just saying, oh, that's a 1 because that base to the first power equals itself. 10 to the first power equals 10. So yeah, if you can understand that, that'll get you helping thinking about logarithms a little bit better. A little bit better. So let's look and see what happens when the base of a logarithm is the same as the argument. The solution will always be 1. And I like how they did it here. They did change a base. They said, okay, well, if it's log base 4 of 4, we can do the change of base and say, well, that'd be the same as log 4 divided by log 4. Oh, so it's easy to understand why that would equal 1. Because something divided by itself is always going to equal 1 if you divide it by itself. So yeah, looking at it through the change of base eyes, it's log 4 divided by log 4 because both numbers are the same. All right, and then they give 3 more examples. We won't do all of these on paper, but you can go back and look at that because there's some videos here. Log base 49 of 343. Write that as a logarithm with base 7. That's where I was getting, where you can choose whatever number you want. If you watch this video, see it's log 7 of 343, log 7 of 49. You can use whatever base you want. Evaluate ln of 4. So ln 4 divided by ln of e, because that's base e. First example. It's hard to see it, but there's a little next button down there. Evaluate log 7 of 15, round to the nearest hundredth. Tenths, hundredths, that's 2 decimals. So change a base. Log 15 divided by log 7. put that in the calculator. So I go through those examples. So those 3 examples are there. If you need to go back and review that, please do, because again, we don't do logarithms very much. All right, so we're going to get into the properties. That's the name of the lesson. Properties of logarithms. So properties, equality property, product property, quotient property, and we have a power property. So I'm gonna write all those on the back of this paper so we can have them all together in one place. And we'll go over these together. So properties of logarithms. Okay, so the first thing they talk about, of course, is log base b of y equals x is the same as b to the x equals y. Okay, that's the first. That's just the basic property of logarithms, how that works. And we had that on the first page. All right, so let's look at the product property. Okay, so the product property says if we have log base b of x and we add to it log base b of y, that will be the same as log base b of x times y. Let's have an example of that. Okay, that's a good thing. We need to do that. So if we had, let's say, log base 7 of 3 plus log base 7 of 5, that would be the same thing as log base 7 of 3 times 5, or log 7 of 15. That's a funky looking little 5. Let's get him looking a little better. Right. So if we have 3 and a 5, we can multiply them together and get the 15. Now, the important thing is same base. Same base. These properties work with the same base. So that's important. I guess I should put that over here just in our notes. Same base. Okay, so there is the product property with an example. I always like to have an example with your notes. Helps us to understand a little bit better, to put some numbers with it and see how it works. I don't want us to get lost in the X's and Y's up here. Let's talk about, a very basic one here before I get to the other properties. Let's do the equality property. This one I kind of call the duh property, but this is the simple. This is not a trick question. This is not a trick property. It really is this basic. If you have log base b of x and it equals log base b of y, then guess what? X equals y. So, for example, if we have log base 7 of 49, that equals log base 7 of x. Guess what x equals? That tells us that x equals 49. Log 7 of 49 has to equal log 7 of 49. Duh. That's kind of, I call that the duh property. Sure, because log 7 of 49 can't equal log 7 of 2. You know, it's got to be, these have, if those are equal, then these numbers have to be equal. These are the same base, equal everything. Yeah. And again, same base. That's the important part there. All right. Right. All right. Product property, equality property. Let's do, let's see the quotient property. Quotient property. All right, quotient. All right, we'll raise this up. We'll get it up on the screen. So that says if we have log base B of X, it kind of goes with the product property here. We added them. If we subtract them, that means we can take log base X and we can, oh, wait. Let me put that down a little bit. I don't want to write that high on the page because it's like this. Log base B of X divided by Y. Same base. Subtracting it, we can just take the argument and divide it. So if we have our example here, log base, let's do base 5 of 42, and we subtract log base 5 of 7, then that's the same as log base 5 of 42 divided by 7, which means it's the same as log base 5 of 6. So that works. 42 and a 7. So we can divide 42 by 7. So it equals 6. And again, has to be the same base. All right, we got one more. We show them all there. Properties of logarithms. Product property. When we add two that have the same base, we can just multiply the arguments. If we subtract two that have the same base, we can divide the arguments. If you have two the same base, they're only equal to themselves. X has to be Y. So the last one we're going to look at is the power property. Power property. And it says if we have a log base B of X to the Y power. Oh, that's a little different. Like, for example, if we have log base 3 of 9 squared, something like that. That means this is the same as Y times log B of X. Oh, so this just moved and went out front. We'll take the exponent and we can move it to the front. So that means this is the same as 2 times log base 3 of 9. But we can do this math because this is the same as log 3 of 9 squared is 81, right? So we can take the log base 3 of 81. Over here, 2 log 3 of 9. Well, 3 to the second power equals 9, right? So log 3 of 9 equals 2. So that's the same as 2 times 2 or 4. So this equals 4 is what it's saying. Log 3 of 81 is 4 because it's the same as rewriting it with the exponent up front, 2 times whatever the log 3 of 9 is. Well, log 3 of 81, let's just check that out. Log 3 of 81. So if we go to the second button, 81 log base 3, it is 4. So this says anytime you have an exponent, you can just move that exponent up front and multiply by it. So I can put it this way if it makes it a little clearer. Y times whatever the log is. So that's kind of an interesting. That's a little different. The y starts up here and it goes out front. And again, you keep the same base. So that's the power property. So I will take a picture of this and put it in Google Classroom. So you have all of these properties there. Hopefully you have it in your notes. But if you lose your notes or if you need to check to make sure your notes are right, I will have this for us to go back and refer to. All right. So let's see how we've done with Buzz here. Same thing. Equality property, log b of x equals log b of y. That means x equals y. So we have that one. Quotient property, that's if you're subtracting, right? Same base. You can just take 40 divided by 8, which is 5. So they have examples of those. The product property was right here. If you're adding them, both of them are base 7, 3 and 5, then it's 3 times 5 or 15. So this page is stuff we just put in our notes. But they do give you some examples. If you want more examples to write down in your notes, there are more. Here's one that uses 3 things added together. It works with 3 things added together too. Log base 8, base 8, base 8. They're all base 8. And this is a 5, a G, and a 4. We can multiply them together. So that's the same as the log base 8 of 20G because we just multiply those 3 things together. So we can do that with more than just 2 logs. We can do that with multiple. Oh, and here's one with an x minus 3. So you might want to watch that video, which is 1:45. And they'll show you how to work with that there. And again, since it's adding, you just multiply it. 6 times x minus 3. And it equals on the other side. So they got it to where it's the same thing. Oh, I really like that example, actually. I think let's do it. Let's actually do that one on paper. Just so we can talk through it. Let's see if we get again, log base 4 of 6 plus log base 4 of x minus 3 equals log base 4 of 24. Okay, I like this one. I like this a lot. So let's actually go through the steps on paper. All right. So the first thing we check is, all right, we're dealing with the same base all the way through. Okay, that's good. That simplifies things a lot. So now on this side of the equal sign, we've just got an addition between 2 logs of the same base. That means we can multiply these. So that's the same as log base 4 of 6 times x minus 3. On the other side, we have log base 4 of 24. Oh, what is this? Well, this is the equality property, the duh property, right? If they're both the same base, log base b equals log base b, x must equal y. This looks a little more complicated, so you may not have recognized that, but what do we have? We have log base 4 equals log base 4. So that means this has to equal this. This is the equality property. So we can drop the bases and say, well, that means 6x minus 3 has to equal 24. So 6x minus 18 equals 24. We add the 18. 6x equals 42. X equals 7. So up here, if we substitute 7 in, 7 minus 3 is 4. So log 4 of 6 plus log 4 of 4 equals log 4 of 24, which is the 6 times 4. That's the product property. That works real nicely. All right, so that's a good example. I like that one. Again, using our properties over here, we can solve that. So, all right, let's go back. See what it has on the next page. I think the next page it has the power property. Yeah, the power property, which we already talked about. If you have 2 to the third power as the argument, you can take the 3 and put it out front. All right. So the power property says log b of x to the y power is the same as y times log b to the x. So that's what we already put in our notes. So they give some examples on this. Oh, here's a good one. 3 log. Oh, that's a really good one. Maybe we should work that. No, there's a different one on work. All right, and there's more examples down here. A review on rational exponents. If you need to review that from previous lessons. T to the 3/4 is the same as the 4th root of t to the third. Remember going back to the exponential rational lessons we had last unit? You know, go back and forth between radical and rationals. So that review there, because we may want to use that in this example. There, let's work this one. This one looks like a complicated, fun type of thing. Mr. Brock, only you would call this fun. Oh, that's base 9. The 9 is kind of high there. Plus 1/2 log base 9 of 64 equals log base 9 of n. All right, so we're solving for n in this problem. So this is our base. We have base 9. Everything has base 9. Those are all 9s. That one's a funky looking 9, but there we go. All right. So how would we solve that? Well, start with the fact that, look, we've got a number out front being multiplied times a log. All right, just looking at that one right there. So this is the power property. If we reverse the power property, that's the same as log base 9 at 216 to the power of 1/3. Right? Because we can just take that and put it back as an exponent. Same thing here. Log base 9, 64 to the 1/2 power. Log base 9 of n. So there's a reason they just did that review on rational and radicals. Because we know that log base 9, this is the 3rd root of 216. Plus log base 9 square root of 64. Since that's a 1/2, that's the square root. Log 9 of n. So what is the square root of 216? What times itself 3 times equals that? 6 times 6 equals 36. 36 times 6 equals 216. So this is 6 to the 3rd power. So this is log 9 of 6 plus log 9 of square root of 64 is 8. We have the product property right here. That means this is the same as log 9 of 6 times 8 equals log 9 of n. Now we got the equality property, n equals 48. So that's the solution to this thing up here, n equals 48. But we had to use the power property, change those from exponents to radicals, solve the radical, and then use the product property followed by the equality property. So we use the power property, the product property, and the equality property to solve that. And ended up with 48. That's kind of fun. What did they get? 48. What do you know? N equals 48. So if you need to go through those steps again, they talk about it here as well. And then page 5, which I think is the last page of the lesson, solving with constants. Log 7 of x equals 3. That's the same thing as 7 to the third power equals x. And so what's 7 to the third power? Another example down here. This is another one that has the 1/2. So it becomes 36 to the 1/2 power, which is the square root of 36. There's more of that. But here is the lesson summary, and it has all of those properties that we looked at. The change of base formula, which we saw early on, the equality property, the product property, the quotient property, the power property. And then with constants, this just uses the rearranging it. Log 7x equals 3 means 7 to the third power equals what? And you take 7 to the third power. So that goes back to the very beginning where we learned how to write a logarithm as an exponent. So we already know how to do that as well. All right. You'll notice that we are far from the end. That means there's several pages of practice problems. So if you're like, I think I understand it, but I'm not sure, this is where you go figure that out. Can you get the right answer there? Here's 3 problems right here. Select the correct choice and then submit. Log 4 of 8. 4 to what power equals 8? Use the change of base formula. Put that in a calculator. Log 8 divided by log 4. Which one of those numbers do you get? I bet you get that one. Yeah. Log 8 divided by log 4. Go to the next one. Here's another one. Log 12, base 12 of 20. Which number do you get? That one's a little trickier. Not on your calculator, just guessing. It's a little trickier to guess than the last one. So you have those. Then you have another page over here. More practice problems. Write log 215 as a log with base 8. So that means the base should be 8 on both of those. And where does the 2 go and where's the 15 go? So this is seeing if you can use change of base. So put the numbers where they're supposed to be and hit submit. See if you're right. Okay, more practice over here. You start getting the properties over here. That was change of base. 1, 2, and 3. So here's 3 different sets of practice problems on the next page. Log 6 of x plus log 6 of 8 plus log 6 of 5, which means that's the product property. It means you can multiply all those together. So you get log 6 of 40x, right? 5 times 8 is 40 times x is 40x. Submit. Yes. 3 problems there. Then you have these problems. This one has the product property and the quotient property. Work that. Over here, some more. And again, I don't know if there's any other thing down there besides that or not. A quotient product. All right. And then page 9 has some more. Should get into the power property over here with some of those practice problems. Again, 3 sets of practice problems. This has a lot of practice problems that will show you the answers if you struggle. If you don't know, if you did it right, it'll show you all the work. Oh, there's a power property. It's got a 2 out front. Check your work. Tells you how to do it. So do enough of these to be comfortable. You don't have to do them all, but do enough to try some of each property and to be comfortable. Let's look at the lesson, the assignment for this lesson. The assignment says, evaluate this. Log 3 of 9. What's the answer? Log 6 of 14. Log base 6. Natural log of 5. That's just punching it in the calculator. Right? A lot of these are just get your calculator. There's a calculator built in right here. If you don't have a calculator, there's one built in. Ooh, boy, maybe change my color scheme. Purple's not good, but there's a log button right there. So I can do change of base with that log button. And this one, I hit log first. And then you type it in, and it shows it log 100. Log 100 equals 2, because 10 squared is 100. So on this one, you hit the log button first. On the Buzz calculator, hit the log button first. All right. How do I make that go away? I guess it stays there. Oh, it's over here. Over here. X. Okay. So you have 10 problems. So it deals with all those different properties. 10 problems, but your calculator is built in right there if you don't have one on your desk. All right, let's look at our second lesson. This won't take as long because we're going to be using properties. Solving exponential equations with unequal bases. All right, so how do we do it if the bases are not equal? Because everything we've done up until now has the same base. All right, so now we're going back to look at this interest formula. And it's going to be a little bit different because let's see, if I write down the problem they're doing with our formula, A equals the principal 1 plus the rate divided by the number of times per year. And so their problem says we want to earn $2,500 to get a new car, a down payment. And we're going to put $50 into savings. So if we start with $50 and we get 3%, that is compounded monthly, how long will it take? So what that looks like is this problem here. Starting with this formula, if we want it to equal 2,500, starting with $50 at a rate of 3 cents, 3%, 0.03, 3%, compounded monthly, so 12 times a year, 12t. We're trying to figure out how many years is that t. We don't know how to do that. We don't know how to solve when it's an exponent. Well, that's where the logarithms work. Answer. Yeah, this is talking about what are all those variables? Principal, interest rate, number of times interest earned. And if we substitute it in there, we get the, oh, well, they went in and did some solving. Okay, we can do that. So they simplified this further. So we can simplify it further by just doing the math. 0.03 divided by 12. So 50 times 1 plus, what is 0.03 divided by 12? That's 0.0025 to the 12t. So this is 50 times 1.0025 going to equal $2,500. When will that equal $2,500? So that's as far as we can go right now until we can figure out the 12t part. So that's where they got it. 50. Oh, yeah, we can divide the 50. I guess we could do one more step. I see what they did. Since this is being multiplied by 50, we can divide by 50 just to make it simpler. So this is 50 on this side, and this is 1.0025 to the 12t. Okay, that's as far as we can go. So how many years would that take to where that interest would equal the 50 over there? All right. Let's look at this, solving equations with unequal bases. These are all base 10. Let's go over here, because that's giving us examples of what we already know. Okay, this is good. Step 1. When you have, I'm going to write this down on paper as they do in here. 4 to the x equals 7 to the x plus 1. Okay, so the first thing they want to do is write that as a logarithmic equation, right? So if we have 4 to the x equals 7 to the x plus 1. Two different bases. This is an exponent, but two different base exponents. We write this as a logarithm. And notice I'm just doing base 10 because that's easiest. The exponent is x plus 1. So now with our power property, we can bring these out front. So this is x times log 4 equals x plus 1 times log 7. Well, your calculator can do this because this is when I put the log in front, I just chose base 10. So what is log 4? Let's see. Log 4. Oh, I divided by 12 now. Log 4 is 0.602. So this is x times 0.60. Let's go. We'll go 5 decimals. So it'd be 0.60206, since those are 9s. Equals x plus 1 times log 7. Well, what's log 7? 7 log. So that's 0.845. Let's see, the 9 is going to round up to a 10, so that'd be to 1 0. Okay, now we've got all numbers. They're decimal numbers, but they're numbers. So this is 0.60206x. And multiply it by x. That's just the coefficient. And when we distribute this, we got 0.84510x plus 0.84510. Sure. Okay. Let's get our x's on one side. Point 84510x. So let's subtract that. So if we go 0.60206 minus 0.84510. So this is negative 0.24304x equals 0.84510. And we just divide both sides by the negative 0.24304. And we'll see what x equals. So the 0.84510 divided by 0.24304 as a negative 3.50148. Again, I'll just go 5 decimals. That's what x equals. Now, when you do this, since we're rounding, you may end up with like negative 3.497 or something. Maybe your number's real close and not exactly the same as mine. I will accept that, right? Because sometimes it's off a little bit. If it's a multiple choice, you may have to look for something a little different, because if they used a different number of decimals, their rounding can cause it to be a number that's really, really close, but a little different. Let's see what they did. They rewrote it that way. Step 2, how did they do theirs? Another 42 seconds. That's the same thing we did, but they used 10 decimals. They went 10 decimal places. So we'll see what they ended up with. See, they ended up with, stop. They ended up with rounding it to 2 decimal places at 3.48, negative 3.48. We'd have negative 3.50. So rounding, just because they went more decimal places than we did. But still, that's fine. And then they go back and they check it by substituting their number back in there. Putting it in the calculator and see if that equals each other. And it does about 0.8. Example 2. All right, this gets to our interest problem. So when we got to this interest problem, we can work this by doing log of 50 equals log of 1.0025 to the 12t power, which means log 50 equals 12t times log 1.0025, right? Using our power property. I can go ahead and divide it right now if we want to without making it a decimal first. So this is log 50 divided by log 1.0025 equals 12t. So I just divided both sides by this. So we can take this and get a decimal number and then divide it by 12. Now tell us how many years. So let's pull up our calculator and do that. Let's see. All right. Log 50 divided by log 1.0025. So log 50 divided by log 1.025 equals 1566. I'll do 2 decimals here. And then we divide both sides by 12. Divided by 12. So it's going to take 130 years. We'll say 0.6. It's going to take over 130 years for $50 to earn enough interest to become $2,500. Starting with $50, it's going to take a long time to get that much interest. Probably going to need to put more money in there. 130 years. Let's see what they came up with. Yeah, that's what they got. 130 years. All right. If you have base E in natural log, that's a good thing to look at real quick. ln of E, what does that equal? Well, that goes back to what we were looking at before. What base is this? This is base E, right? It's not written, but that's base E. So this is another one of those to where e to the first power equals E. ln E equals 1, because that would be log of E over log of E if we did change a base formula, which anything divided by itself is going to be 1. So it talks about that right here, log of E. So if they're using this E to the 2x, you could take the natural log of each side, because ln of E would just be 1. So 2x times 1 equals a natural log of 30. So instead of doing that to log, it might be easier to do that to natural log, because the E will become 1. ln E is just 1 times the 2x with the power property. Then you can just put that in the calculator, see what natural log of 30 is. And yes, your calculator does have the natural log as well. If it has log, it usually has natural log right underneath it. So you can take 30 natural log and then divide it by 2. So in that one, x equals 1.7. There it is, 1.7. Now it's time to try some on your own. So they give you some more practice problems to do. Goes back to this interest thing here. Let's see. It's representing a lizard population. 14 equals 2 to the t. 12 months of the year. So how does that wrap into that? So they put in the 1/12, all this good stuff. Yeah, let's look at this. All right. If it doubles every month, week, or day, I think if I remember correctly, there's a problem on there's our lesson summary. One of our first problems that we work would be good to do together here. Goes back to this rate of growth or rate of decay. So it's either plus R or minus R to the 1/C. It'll be calculated. So let me go to our lesson assignment here. And here is one of those problems right off the bat. This one, like these, you just put log of both, right? And work that. But I want to work this one with you just to get it started. So you've got $12,000 decreases 6% per year, and they want to know decay per month. Select the correct answer. How much is it decaying per month? It's like, oh, that's a good question. So if it's 12,000, the amount equals starts at 12,000. It's decay, so it's 1 minus 0.066%. And they want to know per month. So we would divide it by 12 and be 12T, but we just want to know per month. So if it's decaying per month, how much? Let's take the 0.06 and divide it by 12. .06 divided by 12. It's going down 0.005. Right? If it's going down 6% per year, it's going down 0.005 per month. What is that as a percentage? As a percentage, see, 1% is the same as 0.01. This is smaller than that. So this is 0.5%. To get that, you could take the 0.05 and multiply it times 100. Multiply a number times 100, and it gives you the percentage, 0.05. That's all this question's really wanting to know. Right there. It's going down 0.5% per month. We don't have to calculate the value of what's it in a year, what's it in 2 years. It doesn't ask that. It just wants to know the rate of decay each month. Select the correct answer. I'm just going to turn that in with one question. See, and it was correct. So there you go. Correct answer. All right. There's just 4 questions on that assignment. So it's a little smaller than the other one. Just dealing with change of base. You have 2 exponents. You just set them as logarithms equal to each other. So if you struggle with that, come to class Thursday. Try those examples first in the lessons where it explains how to do that. And then if you're still struggling, come see me. We'll do something together on Thursday. This is an 8A Friday, so no class for us. So we just have Thursday. If your grade's below 70%, and there's not many of you, if your grade's below 70%, then I definitely will see you on Thursday. Otherwise, guys, have a great week, and we will catch you later. Thanks, Autumn.